Mohammed Saleh, just as the Professor Zulman said. I'm from a PhD student from Kosa University, and I'm here to present my first paper that I wrote about computation of and testing crack growth rates at 20 kHz load frequency. So the computation of the crack growth rates is usually done with the help of a crack growth specimen like this one, where the stress intensities at the crack tip is calculated by this equation, which depends on the load, crack length, and also the geometry function of the specimen. This work within this paper is a part of a EURFCS project named FRECTIC, where we, within the project, are trying to evaluate the testing at different load frequencies. And the goal of this work is, of course, to improve the design of components and technical application used at different load frequencies. One question that we are trying to answer with this paper is if there is any influence of the resonance frequency on the stress intensity calculations. Conventional testing with low load frequency usually requires only static calculations of the stress intensity. But when we are trying to do the ultrasonic fatigue testing with the 20 kHz load frequencies, then we believe that dynamic calculations are required. And what we are doing here, we are doing both static and dynamic calculation and for comparison and to see how the difference looks like. Specimen that we are using is a fatigue crack growth specimen for the ultrasonic testing. The rectangular cross-section gives us a plane surface to observe and measure the crack on. The sinusoidal part in the middle reduces the resonance length of the specimen, makes it shorter. And we've also introduced a notch acting as a crack initiator. The depth of the notch is 1 millimeter with a radius of 0.5 millimeter. And with these dimensions, we will have a resonance frequency for this specimen at 20,038 Hz, which is well inside the limits of the ultrasonic fatigue testing. The material that were used for the experiment presented in this paper is a ferritic high-strength microalloy steel with a yield strength of 590 and tensile strength of 870 megapascal. And the chemical composition is shown here. So it's only one experiment that are presented in this paper, just so we can see the results. This paper is mainly about the modeling and not about the experimental work. Experimental setups, just so we can see how our setups look like. We can see the ultrasonic fatigue testing machine with the horn and oscillator up here. Here we have our specimen, and here we have a camera pointing at this plane surface in the middle, where the camera is connected to a computer software where we can measure the crack length. And we are also using a cooled air to cool the specimen while testing. This kind of testing is a displacement controlled testing, meaning that what we are controlling here is actually the displacement U0, and this displacement is just at the bottom of the horn. So by controlling the displacement at the bottom of the horn, we can control the load of the experiment. The load ratio for the experiment presented in this paper is -1. This is a picture of how the crack looks like on the computer screen. What you can see here is the notch and the crack initiation just here. This crack is about 0.5 millimeter long. What we are doing during the experiment is that we are trying to get the crack initiation from the beginning by increasing the load in steps until we get the crack initiation, and we will try to stop it after approximately 0.5 millimeter, and then change the load and keep the experiment running in intervals of 0.5 millimeter, where we will change the load after each step. So now I'm going to talk about the modeling that I have been doing in this paper. First of all, we try to model the frequency dependency on the crack growth. We know that when a crack grows within the specimen will become longer during vibration, and when the specimen is longer, then the resonance frequency will drop. As we can see here from our experiment, where we measured the frequency along the crack growth, what you can see on the x-axis is the crack length, and the resonance frequency of the specimen on the y-axis, and you can see that the value of the frequency drops when the crack grows. So we try to find a model to predict this dependency of the resonance drop. So we tried different methods to calculate the resonance frequency. The first method is a simple eigenfrequency analysis in FEM software abacus, where we're using a quarter symmetry of the specimen. What you can see here in the picture is a zoomed in part close to the notch, and because we're having quarter symmetries, what you can see here is the symmetry line. And this part, just right here, we have the crack tip, and this part that's going down below the symmetry line, meaning crack surface interpenetration. And this is because of the fact that we cannot add any constraint to this eigenfrequency analysis. So that's why we're getting this crack surface interpenetration. And this will, of course, cause a problem, since that's not what's happening in the experiment. The crack surfaces are not penetrating each other. And the results of this method showed a clear difference from the experimental result. The drop of the frequency is much faster than from the experimental results. So we came up with another idea, which we call the pull and release method, which is basically a two-step method, also within FEM software abacus, where in the first step we simply just pull the specimen in a static step, and in the second step release it in a dynamic step and let it bounce back and measure the time for each bounce, and from that we will calculate the frequency. What was good with this method is that it allows us to add stuff to the model, like a rigid element blocking the crack surface from penetrating. So we don't have any crack surface interpenetration for this model, pull and release method. And the result from this one showed a slight increase in the frequencies, but still not quite there. There is still something missing to get up to the experimental result. So we tried another method, which is the calculation of effective natural frequency, modeled by Shakti and his co-workers. It's about calculating an average value of two different resonance frequency, omega 1 and omega 2. Omega 1 is the resonance frequency of an uncracked specimen, and omega 2 is the resonance frequency of the cracked specimen with a specific crack length. So with the help of this equation, we can calculate the effective natural frequency for all crack lengths, and the result from that agrees almost perfectly with the pull and release results. And what that says is that these two methods actually confirm each other, and we can trust them somehow. But still, there is something missing to the experimental results. So we needed to do something else. And we started to think of the idea that these results are actually, these frequencies are actually not the frequency of the specimen, but rather the frequencies of the whole system, including the oscillator and the horn. So we tried to, in the last step, to include the oscillator and the horn into the model, FEM model, which will look like this, where we have the specimen down here and the horn and the oscillator. And the oscillator is represented by a solid cylinder with a 20 kHz frequency, resonance frequency. And as you can see here, we are not allowed to have the symmetry here anymore, since we've added some parts on the top of the specimen. So for this model, it will be only half symmetry. And we will not be able to avoid the crack surface interpenetration here. And therefore, we are going to use Schottky's effective natural frequency even for these results, in order to get rid of the crack surface interpenetration problem. And the result from this last model agreed almost perfectly with the experimental results, where we have the effective natural frequency, including the oscillator and the horn. So with this model, we accepted this model, and we did not try to improve it further. Now to the stress intensity calculations, where we are using this equation constructed by Wu and Matias. What this equation does is basically connect the displacement U0 to the stress intensities at the crack tip. The stress intensities are calculated within this paper, both with a static analysis and a dynamic analysis, just as I mentioned earlier. And the result of that we can see represented in this graph, where the first orange boxes represent the stress intensities from the static analysis, and the green triangular markers represent the dynamic analysis with 20 kHz load frequency. And after that, we decided to actually include the horn and oscillator even here, since we knew that it improved our frequency model. So we decided that we will include them even here in the stress intensity calculation model. And that gave also a dependent frequency, meaning that every simulation had its specific resonance frequency. The difference between static and dynamic calculations, what we can say is that the stress intensity calculated by static analysis are about 30% lower than the ones calculated with dynamic analysis. The next step will be to take the values calculated, the stress intensity values calculated, and to use this equation in order to calibrate the geometry function, this function. You need to calibrate it in order to get the function which will be valid for all A's, not only the specific crack lengths, but rather for all A values, all crack lengths. And if you use the dynamic results, the red boxes, we will get this geometry function, and if you would use the static values, then we would get this geometry function. And we can see that they have different values, but much more than that we can't really say about it. Lastly, we will take this geometry function, which is valid for all crack lengths, and reuse this equation in order to produce a calibrated delta K, which is also valid for all crack lengths. And this blue line here represents the calibrated delta K from the dynamic results. And as you can see, it's a homogeneous line and it's valid for all A's. So now we can use this calibrated delta K during our testing. This is a fracture surface from one of our specimens, where we have the notch here and we have a crack initiation. The first part is the fatigue fracture, and the last part is a final fracture. But we can see here that I've divided the fatigue fracture into two parts, delta K decreasing and delta K increasing. As I said, when we're trying to get the crack initiation, we are increasing the load until we get the crack initiation, and then in steps we will decrease the load until the crack stops to grow, until we don't get any crack growth anymore. Then we will start to increase the load again. And maybe I should also mention that as expected, we could see the normal fracture surface with the striations within the fatigue fracture surface. The experimental results I showed here, what I'm showing here is the result from both dynamic and static crack. This is the crack growth rates, the N versus delta K, where we're trying to fit to the Paris law, and the result from the dynamic calculations. You can see that C and is equal to 2.86, and the threshold value is around 4.1. And from the static, we can see a higher C value, which means that it's shifted to the left, but almost the same N value, which means the same slope. And the threshold value is a bit smaller, 3.1 megapascal. The conclusions, I can conclude that we have an acceptable model for the frequency dependency on the crack lengths. And we also see a clear difference between the static and dynamic calculated stress intensities, but we can't really say, not yet at least, which one is the best one. We need further investigation to really conclude whether the statically calculated stress intensities are better or worse than the dynamically calculated stress intensities. And finally, I will thank you, the European Union Research Fund, for coal and steel, for funding this project. And thank you for your attention.